Welcome to this video on Ampere's law and a particular application in computing the magnetic field in a coaxial cable. This may be extended or modified to find the magnetic field around a single wire as well. It all started in 1820 when a Danish physicist Oersted observed that the needle of a compass kept next to a current-carrying conductor turned. On further investigations, a few more observations were made, in particular that the strength of the field was directly proportional to the magnitude of current in the conductor, and that as distance from the wire increased, the strength of the field reduced. Based on Biot-Savart law, and equivalent to Coulomb's law in electric fields, Ampere proposed the force law, which computes the force between two current-carrying conductors. Later, in 1865, Maxwell came up with the Ampere's Circuital law, which states that closed line integral of magnetic field intensity is equal to the current enclosed. This essentially means that if we have a magnetic field and we compute the total around a closed line, this is going to be pretty much equal to the total current within this closed path. Moving forward, let us consider a coaxial cable. Now, a coaxial cable is essentially a pair of cables which share the same axis. So there are two current carrying conductors arranged in such a way that the axis of both current carrying conductors are the same. Assuming the inner conductor to have a radius of A and the outer conductor to have a radius of B with a thickness T, there would exist an electric and magnetic field within the space between the inner and the outer conductors, as shown in this figure, where the blue lines would be the electric field and the purple lines would be the magnetic field. Let us try to compute the magnetic field within the cable. We further assume that the coaxial cable is placed on the z-axis and the inner conductor carries a current I in the positive z direction. Naturally, the outer conductor would conduct the same current I in the opposite direction, that is the negative z direction. This may also be considered as a current negative I in the positive z direction. Upon closely observing the scenario, we understand that the cylindrical coordinate system would be best to describe this situation here. And since the current is in the positive z direction, we observe that there are different cases where magnetic field is going to exist, right from the distance from the z-axis being equal to 0 going outward, radially outward. And since the magnetic field component is going to be circular, we find that the component of interest is h phi and the variations of r is going to be from 0 all the way outwards. Since the inner conductor has a radius of A, the outer conductor has a radius of B with a thickness of T, as in when R is less than A inside the inner cable, as in inside the inner cable, or R being less than or equal to A, outside the inner cable but inside the outer cable, that is the distance R being between A and B. Now this would be the field intensity in the dielectric. Within the outer cable, so somewhere over here I would say, and outside the outer cable would be at some distant point P. Having said that, let us look at case 1, that is inside the inner cable. So zooming in into the inner cable, we find that at from Z, the entire radius of the cable is A. Let us try to compute what the magnetic field intensity is going to be at a distance of, say, R from the Z axis, where R is less than A. So at this point, if the radius of the inner cable is A, we are trying to looking at Ampere's law, the left-hand side being a closed line integral, and upon observation we find that the closed line integral takes the shape of a circle, and hence the integral is going to take a value of 2 pi r, or the circumference phi, the magnetic field component of interest, times 2 pi r, enclosed within the area of the right hand side states current enclosed within the area of consideration. Now this may mathematically be written as the surface integral of current density. The total current is going to be the surface integral of current density. Now the current density in divided density being defined as the quantity per unit area, the current density in this case is going to be the total current divided by 2 pi a squared, where the inner conductor's radius is A. Hence, the total current enclosed may be written as the surface integral of A squared ds. Equating the left hand side and the right hand side, we find that h phi 2 pi r is going to be equal to the surface integral of I divided by 2 pi a squared. Now ds being cylindrical coordinate system, in the z direction is going to be r dr d phi. Hence we have to perform two integrals, one on r and one on phi. The limits on r being from 0 to this particular point r, so from 0 to r, and the limits of phi being from this point all the way around to this point, 0 to 2 pi. Hence on performing this in out, so 1 by 2 pi is r squared by 2, turns out to be r squared by 2 itself, and this turns out to be 2 pi divided by 2a squared on the right hand side, with an r here and the square cancelled out. I am going to say that my h phi is equal to I divided by 4 pi a squared in the a phi direction. Now, since the magnetic field density is equal to the permeability times magnetic field intensity, I may as well rewrite this equation as magnetic field density is equal to mu 0 I times R divided by 4 pi a squared. In a case where we move outward, further outward from the inner conductor, we observe that the left hand side is going to be the same, h phi 2 pi r, where r is greater than a. We observe that the total Amperian current enclosed within this shaded area is equal to the total current in the inner conductor I. Hence, the magnetic field intensity is going to be I divided by 2 pi r in the a phi direction. And as we wrote earlier, the magnetic field density is going to be mu 0 I divided by 2 pi r. Now this is because the Amperian current enclosed is equal to the total current in the inner conductor. Moving further to case 3, where we move into the outer conductor, the left-hand side of Ampere's law turns out to be the same, h phi times 2 pi r, where r right now is between b and b plus t. Now to compute the right-hand side of the current enclosed. Upon observation, we find that the entire inner conductor current I will be considered, and a part of the current through the outer conductor needs to be considered. So plus I dash, where I dash is a part of the current through the outer conductor. Now part of the outer conductor may be computed as the current density, the surface integral of current density through the outer conductor. So for that we need to compute the area of this particular point here. So for that we've got to compute the area of the outer cable. Now to compute the area of the outer cable, we see that there is this distance here which takes a value b plus t, and we have this distance here which takes a value of b. So the area of the outer conductor is going to be the outermost area, being b plus t the whole squared, minus this area here being pi b squared. Or in turn, the area of the outer cable is going to be pi times b plus t the whole squared minus b squared. In that case, the current density here is going to take a value of I plus surface integral of current divided by pi times b plus t the whole squared minus b squared. Now let us go ahead and compute this total current. And we observe that, the outer current moves in the minus AZ direction. So getting all these facts into place, the right hand side is going to take a value of I. Now since this is the direction is minus AZ, I can as well assume I to be minus I in the plus AZ direction. So I'm going to minus here the surface integral of I divided by pi times b plus t the whole squared minus b squared, obviously in the r dr d phi surface. So my R is going to take values from 0 to R, which is going to be between B and B plus T, and phi is going to take values from 0 to 2 pi. Upon computations, we find that we need not bother about this guy here. So we have the entire component I minus I divided by pi times B plus T the whole squared minus B squared times R integral is R squared by 2 from 0 to R, and phi d phi integral is going to be 5 with limits 0 to 2 pi. So I see that I have is equal to, from this, let me go ahead and take an I outside, 1 minus 1 by pi times B plus T the whole squared minus B squared times R squared by 2 times 2 pi. Pi 2 and 2 cancels out, and I have H pi equal to I divided by 2 pi R times 1 minus 1 divided by, or R squared divided by B plus T the whole squared minus B squared. Equivalently, B is going to be mu times I divided by 2 pi R times 1 minus R squared divided by B plus T the whole squared minus B squared. Moving further outward of the outer conductor, we see that the left hand side again is the same old H phi times 2 pi R, but the right hand side is going to have to consider the full current through the inner conductor plus the full current through the outer conductor, being I in the plus AZ direction and I in the minus AZ direction, turning out to be 0, or H phi outside the outer conductor turns out to be 0. To quickly summarize, we see that inside the inner conductor, the magnetic field intensity is directly proportional to the distance from the center. So if we just try to plot the magnetic field with distance, we see that inside the inner conductor, or till R is equal to A, the magnetic field is directly proportional and increases linearly with the R, because in this condition here, H is directly proportional to R. And we can as well say that the maximum value here is going to be I divided by 2 pi A, assuming R equal to A. Moving further out, we see that in this case H is proportional to 1 by R, or inversely proportional to R. That is, as we move out of the inner conductor, the magnetic field intensity is going to reduce as 1 by R. And as we move further out into the outer conductor, the proportionality is more complex but significantly reducing. It is some quantity minus some other quantity. So it further reduces. And the moment R moves out of B plus T, the value reaches 0. So this is how the magnetic field intensity within a coaxial cable is going to look like.